Okay, welcome everybody to Physical Science. This is the conclusion of the notes for this chapter, forming chemical equations. I think you'll like this a little bit. So we're going to show you a little bit different way to write ionic formulas, or formulae is the correct plural in the Latin form. So writing ionic formulae. Oxidation number, so you got to get out your periodic table so I can show you where your oxidation numbers are. Now that you have your periodic tables out, you can see the bottom left-hand corner has the key. Do you notice where it says oxidation states? Yeah. Okay, so for zinc, what does it say in your periodic chart? 2, right? Okay. Okay, so what's the oxidation number for francium, bottom left-hand corner, the normal plot? Very good. How about, let's say, calcium?
2.
Notice, beryllium, magnesium, calcium, strontium, barium, radium, they all have how many valence electrons?
2.
And what is their oxidation number for all of them?
2.
2. Did you notice that?
Yeah.
What do you guess the oxidation number will be for the group 1?
1.
1. Are you right? Look. It looks like 1, right?
So oxidation is...
But now look at this. I'm going to explain it more. Hydrogen, notice hydrogen has not just 1, but it has plus 1 and negative 1. So hydrogen can act, hydrogen special can act in more than one way. Notice it's a gas, but it acts like a metal too. Okay, so let's look over on the other side of the periodic chart. What do you expect your oxidation numbers will be over there? Okay, over here on the other side then, well, first of all, helium, neon, argon, krypton. Well, krypton is where we first start seeing a couple oxidation numbers. You see that? Krypton has a 0 and a 2. You see that? But the other noble gases don't. What's the deal with noble gases? They don't what? React, right?
Yeah.
They don't react. They don't form more compounds. But according to this, krypton on down do sometimes. Now, look at fluorine. So group 17. How many valence electrons? 7. What's fluorine's oxidation number? It's -1, right? Or on the other side, it was a positive 1. Do you agree?
Yeah.
So when it oxidizes, it's going to get 1 extra electron. It's going to have a -1 charge. Think about the other side. Okay, so the other side of this chart, when this reacts, when sodium reacts, oops. When sodium reacts, it gets rid of an electron, and it has a +1 charge. Are you starting to see the pattern?
Yes.
Okay, so when calcium reacts, Grant, how many electrons does it give away? 2, right? Leaves it with a +2 charge, right? Look at the oxidation number. +2. Let's go to the other side of the table. When oxygen reacts, so here's oxygen. When it reacts, it takes on 2 electrons, right? It has 6. To get 8, it takes on 2 more, which gives it a -2 charge because it has 2 extra negative charges. Remember that?
Yep, and then why is there a -1 as well?
Well, look at the first one. We're going to deal with the first number only. Okay? Because, is it -2?
Is it because it's like the second one?
When it reacts, if it reacts in an ionic equation, or in an ionic situation, it's going to take on 2 negative electrons, which is it means it's going to have a -2 charge. That's what the oxidation is. What do you see for nitrogen? Well, it says plus or minus 3. Okay, so I want you to think of just the first oxidation number when we talk about this. Okay, so let's go back to the notes then. Okay, oxidation number tells how many electrons are gained or lost from an atom to be stable. Okay? So keep in mind, I want you to look at the first number to start out with, and then you guys will know if it's gaining or losing electrons because of where it's placed on the table. Okay, let's see here. Main block elements are determined by group number. So this is what we've already done. This is what we've already done. Group 1 loses 1 electron. So what's its oxidation number going to be? Plus 1, very good. Plus 1, since the charge is 1 positive because it lost 1 negative, leaving it with 1 more proton than electrons, giving it an overall plus 1 charge. So what would you think of group 2? Plus 2, right?
Yeah.
Group 3 or 13, depending on what chart you're looking, plus 3. Group 15 is negative 3. Now notice we don't have 14 in there. 14 can go either way, so it can go plus or minus 4. But it's not real common that it reacts in an ionic situation. So we don't even put that in there. In fact, I don't know when it ever does. Group 16 is going to be negative 2, 17, negative 1. And group 18 is not there either because it doesn't react.
Oh, okay.
The noble gases don't react. So there's no real oxidation number there. Okay, so transition elements are labeled in the periodic chart. So everything's labeled in the periodic chart, but we don't have to use the periodic chart for the main block elements because we already had that memorized. Because you know how many electrons they gain or lose just by the group that they're in. So let's look at the periodic chart for this piece. Okay. So if you look here in the transition elements, I'm going to erase some of this highlighting here first. Okay. So chromium, look, it has, 3, 6, and 2 right there in 24. Iron, this is a pretty common one, 3, 2, and 6. But remember how we said that, before we didn't really talk about these because we were just looking at the patterns of the normal block or the main block. But now we can start to use these transition elements or metals because we can look at the oxidation number on the periodic chart. Okay, so scandium is 3, zirconium is 4, niobium is 5 is the first one. Rhodium is, what do you guys see for rhodium? 2, very good. Nickel is 2, very good. Copper is 2. Okay, so notice there's a bunch of them here that all have 2 right in a row. Okay, so you'll learn more in chemistry why that happens, but for now we will just use our periodic chart in the first one. Okay, so number 3. Some elements have more than 1, which we just said. Like, I want you to use the first one, with the exception of the ones I have here. So iron, because commonly it can have 2 or 3, and copper can have 1 or 2. So notice this. When you have iron 2, that means plus 2. When you have iron 3, Roman numeral 3, that means plus 3. So from now on, you're going to have to tell the difference. If it says iron, Roman numeral 2, that means you're given the iron that oxidizes at a plus 2 or gives away 2 electrons. Iron 3 is going to give away 3 electrons, so it has a plus 3. And then copper 1 and 2 also have these multiple oxidation states. So what you have to know about this is if there's a Roman numeral, that is the number that it oxidizes at, or the number of electrons it loses. Okay, polyatomic ions we talked about already. It's many ions, or many atoms making one ion. That's on a chart. And this is the chart here. Okay, so this chart is on Moodle for you. And I will allow you to use it. So you did memorize some of these, so you got used to seeing them. But there's so many of them, I'm going to allow you to use these for the test.
Wait, what? So this is-
So these are all like acetate, C2H3O2. And notice, this whole group here has a -1 charge. This whole group has -3, and in the middle is all -2.
We have to memorize it for the test.
No, you'll be given this chart to use for the test. But what this means is this whole group, like if we're looking at this one right here, CO3. So the important part of this is that you realize that this CO3 is a group. So if I would draw the atom, it would look like this. And it'd have a partial double bond in all these places. And this whole entire polyatomic ion, this whole group is sharing 2 extra electrons. So this whole group acts like, just like oxygen would. You know how an oxygen, when it oxidizes, it takes on 2 electrons? One oxygen can have this charge of -2, just the same as this whole group of atoms has a charge of -2. So this is going to act like just one piece. That's why it's called polyatomic ion, because it's many atoms that make one ion. Okay, so you'll be able to use this chart. So you can either download it or I'll print it out for you. So polyatomic ions, they have their oxidation numbers on the chart. Okay? So now you're going to like this part. But I don't start with this because you need to understand why this is happening and why it's okay. So I start with something other. Okay, so I lost my shade for some reason. But B, using oxidation numbers to write ionic formulae. And then to go on, it says, all chemically stable compounds will have no net charge. Therefore, the sum of the oxidation numbers must equal 0. So if you understood well what the worksheets were, what we were doing with the worksheets, we had +6 and -6 on the other side. You know what I'm saying? Or +2 and -2 on the other side. Do you know what I'm talking about when we put our ions together? Same thing with this, and that's all this is restating here for you. Okay, so here's kind of instructions on how to do this. When you write the formula, I always write the least electronegative element first, which is basically just go from left to right on the periodic chart. Or if you have the polyatomic ions, you put the positive ones first. So you could always just say the positive ones come first. Now, is it wrong to write it the other way? Well, it's not really wrong. Because if you were looking at an atom from the front and someone else was looking from behind, it would be in the reverse order. It's not really wrong, but you might as well get in the habit because they're always written with a positive, or what we call the cation, in the first position. Okay, so the definition of electronegativity is the atom's attraction to the electrons, and we've talked about this a lot of times already, and it increases as you go to the right and up the periodic chart. So if you will look at the periodic chart, this would be, this right here, francium, would be the least electronegative.
Helium would be the most.
Well, fluorine is the most. So these guys are kind of in their own group because they're noble gases, they don't really react.
They're like
They kind of separate.
they're like the stuff.
They separate, yeah.
That's the
So it goes like this. as far as electronegativity. And you'll see there's a number for electronegativity in your chart too. It is, maybe there isn't on this chart. I think it would be on the back side of this chart, which I didn't print out for you. Okay. So does it make sense that up here, fluorine's going to have the biggest attraction to electrons, so it's going to add electrons. This is going to have the smallest attraction, it's going to give away electrons. So what happens if you look at the atomic radius, do you remember that little picture we had last time we talked about the atomic radii? Okay, so here's the atomic radii of the normal block. This doesn't include the transition elements. But look at this one, cesium. And it's got, actually, I guess, let's see here. Yeah, cesium here, it's huge. And so if you think of the protons in the very middle and these electrons out here, and you think of the force of electricity and the radius, it's an inverse square. So when we get further and further and further away, then we get further in this direction, and we get much less force of electricity. And that would be the electrons attracting to the protons in the middle. So the electrons that are on the very edge here, they're barely held into place by the attraction of the protons. But look at this up here. Fluorine here is really, really, really small. And it has a lot of protons and or it doesn't have a ton of protons and electrons, but the smaller you are, here's your same force of electricity, then you're going to be in this position where there's a very strong attraction of the electrons, the outer electrons, or the valence electrons to the protons, because it's so much closer. And so that's where this all comes about, is this force of electricity and how close the valence electrons are to the protons. Okay, so if we look at this next piece, so the first part we went over. The second part of writing these is you write the atoms that are going to be combined. So this is basically what we already did. Write atoms that are going to be combined, including the oxidation numbers. So this is different from before because we wrote the valence electrons. Now we're just putting the oxidation numbers. So for instance, let's look like this. Na plus 1, Cl negative 1. Okay? I'm just going to show you what to do. It's called the crisscross method. So you put that subscript there and that subscript there, and here's your formula, NaCl. See how easy that is? You're going to like this one. Let's see, what did we do? One that was a little bit harder. We did like Mg and N, right? So we did Mg, which is plus 2, and N, which is negative 3. Is everybody following me here? Know where I got those numbers from? Okay, so this plus 2 here is really signifying that it's going to give away 2 electrons. Do you agree?
Yeah.
Because before when we did this, we had Mg and we had 2 electrons, and then we had nitrogen with 5 electrons, and we said, hey, this goes here, and this goes here, right? Leaving the Mg as a plus 2. And then we had to do another Mg because nitrogen wasn't happy, and we had to keep going back and forth. Remember that?
Yeah.
But now look at how easy it is. Crisscross method. Mg3 and 2. And there's your formula. So it's much, much easier, but the understanding comes from this piece more than just this little pattern of trying to write the correct chemical formula. So that was a good question. Why isn't it negative? Well, we're not writing the oxidation or the charges, but if we were to write the charges, 2 nitrogens, they each took on 3 extra electrons. This side would have negative 6, right? And then this side would have positive 6 because 3 magnesiums gave away 2 electrons apiece. Does that make sense? Okay. So let's look at another one. Let's say that we have magnesium and oxygen. Okay. So this is going to be a +2 and this is a -2. Do you agree? If you use the crisscross method, you would get Mg2O2, but I'm here to tell you that's not okay. Because if it's an ionic compound, then you use the smallest whole number ratio of the atoms. Because they come together as a bunch of positives and negatives. So the correct answer for this one is just MgO. Okay? So if you have subscripts that are divisible by each other, then you have to simplify those if it's an ionic compound. If it's a covalent compound, it's a different story. This is just for the ionic compounds. Okay, so let's look at what we do if we have a polyatomic. Okay. So let's take carbonate. So we have CO3, and together it's a -2. Okay, so it's very important that you put this down. Like this is part of your notes. I'm explaining the notes to you that are written. This is better. So CO3 -2. Let's say that we're putting sodium with it. Okay, I would put the sodium in front though because it's positive. That's a +1. Do you agree? Any ideas where I got these numbers, or any questions where I got these numbers from? So the correct formula for this then is Na2CO3. Although you probably wouldn't, this isn't wrong, but you would more commonly see it like this, Na2CO3, because you don't need parentheses if there's no subscript for it. Let's try another one. Okay, let's go Mg, which I know is a +2. And we'll say PO3, which is a -3. Questions where I got those numbers?
Yeah, where did you get that?
If there's more than just 2 atoms, it's going to have a polyatomic ion. So you're going to have to say, oh, this has more than 2 atoms. I need to find the polyatomic ion in it. So the PO3 is that group that acts like one thing. Which all of these on this sheet, like this, phosphate, that acts like one thing. Carbonate acts like one thing. And phosphate is what I'm doing. Okay, so if we do the crisscross method, then you have Mg3, PO3, 2. Okay, so that's, if I didn't put these parentheses here, then it wouldn't be signifying that the whole group of PO3 is 2. It would just signify something different.
So the Mg3, P2O6.
No, it's Mg3, PO3,
PO3.
but 2 of those.
Oh, 2 PO3, PO3.
You want to try another one? Okay, let's see if you guys can do this one then. Let's do calcium and phosphate. Okay, see if you can do that. Well, let's look at it. Where is phosphate? Did you guys find phosphate yet?
No.
It's right here. Okay. So calcium, we can see off our chart is a +2. Phosphate is a -3. So the answer would be calcium 3. And then the whole PO4 units 2 times. So there's your formula for calcium phosphate. So the question was, how do you get those bottom numbers? Well, I'll show you right here. See this number here? You just put it as a subscript on that side. And this number, you just put it as a subscript on that side. It's called the crisscross method. But keep in mind, if we have 2 of the same numbers, then you have to simplify it down. So if you had Ca2PO4 2, it would be just CaPO4. Okay, so that's enough for you today. We'll see if you can work with this.